Howdy, folks. All right, let's jump back in here to talking about gases and how the different properties of gases are related to one another. So last time I teased that we were going to talk about how the pressure of a gas is affected by three different properties. How the number of moles of a gas has an effect on the pressure, the temperature has an effect, and the volume has an effect. So this is just how many particles are present. That is the number of moles. The kinetic energy of the gas, that is the temperature, and then the amount of space they have to move around in, that is the volume. So let's think about how volume and pressure are related. So, how does the volume of the container affect the frequency of collisions? If you have a tiny container and you put a mole of gas into that container, so we have a container, this size, say here, and you put a whole bunch of gas particles in there. So those are moving around constantly, and because the container is fairly small, they're just going to be hitting the walls of the container over and 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 over, very, very rapidly. And so if you have a small container like this with lots of gas in it, simply because the particles don't have to travel very far to hit the walls of the container again, the pressure is going to be relatively high versus something, this size, where you put the same number of particles into that container, and the particles move around, and yes, they're moving at the same speed there. I'm trying to move my hand at the same speed. You can tell that they're not hitting the walls of the container as often simply because the container is larger. So if a gas particle hits the walls of the container here and then zips off in this direction, it takes at least twice as long to get to the walls of the container again, to hit the walls of the container and provide pressure. So volume and pressure are actually going to be inversely proportional. If we decrease the volume, if we make the container smaller, because there's less room for the gas to move around in, the pressure is going to increase. So they are inversely proportional. As one goes up, the other one goes down. As volume increases, pressure decreases. As volume decreases, pressure increases. So they are inversely proportional. And this is described using what we call Boyle's law. So Boyle's law says that the pressure and volume of a gas are inversely proportional, and that if you multiply the two together, you get a constant. And the more common way that we represent this is a perfectly acceptable way to do it, but the more common way is to write it out like this, where any pressure and volume pair is going to be equal to any other pressure-volume pair. As long as it's the same, you're not changing the number of moles, that's held constant, and the temperature is held constant. So if everything else is the same, the pressure times the volume in one situation is going to be equal to the pressure times the volume in a different situation. You can see that here. We have a sample of gas. It has a volume of 1 liter. It has a pressure of 1 atmosphere because there's a certain amount of pressure being applied to the plunger up here on the top. If we double that pressure, so the weight on the top here pushing down is now 2 times as high, the pressure inside the container becomes 2 times as large because we've added that extra weight there, and that translates into gas pressure because we've scrunched down the size of the container to half of what it was before. So because the volume of the container is half of what it was before, those gas particles don't travel as far before they hit the walls of the container again, and so the pressure is then doubled. So we decreased the volume and increased the pressure by doing that. And so graphs of pressure versus volume are always going to look something like this. They are not linearly related like this, although you can actually get a linear graph if you do 1 over the pressure versus the volume. That will give you a linear graph. But if you're just looking at pressure versus volume, you get a graph that looks something like this. So as the volume is increasing, as we go to the right here, we go to higher and higher volumes. The pressure is getting lower and lower and lower and lower. So let's look at an example here. So I would encourage you to pause the video before I work it out, just to see if you can work this out yourself. So if you're going to do that, go ahead and do that now. All right, hopefully you made an attempt at working through this on your own. Let's go ahead and read through this together. It says a cylinder equipped with a movable piston has an applied pressure of 4 atmospheres. And a volume of 6 liters. What is the volume of the cylinder if the applied pressure is decreased to 1 atmosphere? So notice here, as I was going through, I went ahead and labeled the first set of things that I came across as P1 and V1. And then the second set as P2. And then V2 is actually what we're going to be looking for. Honestly, it doesn't matter which one is 1 and 2. You could have done the 4 and the 6 here as 2 and said that the 1 atmosphere was the P1. The math is going to work out the same. As long as the pressure and volume that go together have the same number, either 1 or 2, it doesn't matter which one is 1 and 2. It's just usually when I do this, I try to have the initial state be 1 and then the final state be 2. But the math is going to work out either way. So Boyle's law is P1 V1 is equal to P2 V2. We are trying to solve for V2. So what we're going to do is we're going to do the algebra first here, and we're going to divide both sides by P2. And that will give us V2 is equal to P1 V1 over P2. And we have all those numbers. So V2 is equal to 4 atmospheres times 6 liters over 1 atmosphere. Notice there that the atmospheres cancel out, leaving us with just liters, which is good. That's what we want. And so that is going to be 24 liters. And we can double check to make sure that our answer makes sense. If we started at 4 atmospheres with 6 liters, the change that happened here is we decreased the pressure. And because we know pressure and volume are inversely related, if we decreased the pressure, then the volume should increase. And that's what we see. So we decreased the pressure, so the volume should increase, and it does. It goes from 6 liters to 24. All right. Let's go ahead and talk about temperature and volume and how these are related as well. So, how does the temperature of a gas at a constant pressure affect the volume of that gas? So it's not only a constant pressure, it's also a constant number of moles as well. So essentially we're not losing gas and we're not adding any gas to it either. We are holding everything else to be constant. The only things that are changing are temperature and volume. And so if we think about what happens with a gas, if you have a gas, you're holding the pressure constant, you're holding the number of moles constant, the only thing you're changing is the temperature. If you increase the temperature of a gas, what's going to happen is that gas is going to get more energy. It's going to get a higher kinetic energy, which is just another way of saying it's going to move faster. Some of that movement we don't care about, like rotational movement, vibrational movement, those will increase, but we don't care too much about that in terms of the gas. What we care about is that not only is it going to rotate and vibrate faster, it is going to translate faster. It is going to zip around at a faster speed. And so what that means is, if we go back to our gas in a box here, at a very cold temperature, the gas might be moving at a speed something like this. Just kind of slowly moves across the container, and that's a bit of an exaggeration, but at a cold temperature it's not moving very fast, whereas at a hot temperature it might just go whoop, just zip right across the container because it has more kinetic energy. And so what that means is, because it's moving faster, it's going to impact the walls of the container more often. And so because it's going to impact the walls of the container more often, it's going to have a higher pressure. It's going to yield a higher pressure. Well, actually, since we're holding the pressure constant, in order to keep the pressure constant, it's going to force the volume of the container to expand. Because if we didn't, then the pressure would increase. But since we're holding the pressure constant, the volume has to get bigger so that the faster moving particles have to travel farther to get to the walls of the container. So if we increase the temperature and wish to maintain constant pressure, the volume has to increase. So volume and temperature are proportional. What that means is that when one of them increases, the other one is going to increase. And when one of them decreases, the other one will also decrease. Whatever happens to one, the same thing happens to the other. So they are proportional. You can see that here in the graph. This is what a graph would look like of a temperature versus volume. As we go to higher temperatures, we go to higher volumes. The gas moves around faster, it pushes on the walls of the container harder, and so in order to keep the constant pressure, the volume has to expand to do that. So the one form of this law, which is called Charles's law, looks like this, where we have the volume over the temperature is equal to a constant. But the more common form is this one, where again we have a initial state and a final state, or just one state versus another state, where we have V1 over T1 is equal to V2 over T2. Now, a word of caution here. When we're dealing with temps with gases, we must use Kelvin. If we try to use Celsius or Fahrenheit, it's not going to work out correctly, and sometimes quite dramatically not correctly. So anytime we're dealing with gases, and we're dealing with temperatures of gases in equations like this, we have to use Kelvin. Kelvin is required. So when we look at this example here, it tells us, and again, go ahead and pause the video if you want to give this practice problem a shot. It will use Charles's law. But go ahead and pause the video if you want to give that a shot before we work through it together. Okay, so we're told in this problem here that a sample of gas has a volume of 2.8 liters. I'm going to go ahead and call that volume 1. It's at an unknown temperature. We don't know what T1 is. When the sample is submerged in ice water, which has a temperature of 0 degrees C, its volume decreases to 2.57 liters. Excuse me. What was its initial temperature in Kelvin and Celsius, assuming a constant pressure and a constant number of moles of gas as well? All right, first thing we need to do here, just talked about it a minute ago, we're not allowed to keep Celsius. We need to change that to Kelvin. 0 Celsius is going to be 273 Kelvin, because if you remember the conversion factor from Celsius to Kelvin, just take the temperature in Celsius, add 273, and since we have 0, it's just going to be 273. Charles's law is the volume over the temperature in one state is equal to the volume over the temperature in a second state. We are trying to solve for T1. So we're going to have to do a little bit of algebra here to get T1 by itself. A very, very common mistake at this point in this problem is students will say, okay, well, I'm just going to divide both sides by V1, and I will have T1 is equal to V2 over T2 times V1. And that is not correct. If you do that, if you divide both sides by V1, you don't end up with T1 is equal to this. You end up with 1 over T1, because the T1 is still in the denominator here. We didn't move that just by dividing both sides by V1. So instead, you can start by dividing both sides by V1. That's acceptable. But then once you get to this point, because we're not looking for 1 over T1, we're looking for T1, we can take the reciprocal of this. And so there's a couple different ways you can think about that. If you want to just trust me, essentially what we're going to do is just take the whole thing and flip it. So everything that's in the numerator goes in the denominator, everything in the denominator becomes in the numerator. More mathematically speaking, what we're saying there is we're going to divide 1 by everything on each side. So we would have 1 over T1 is equal to 1 over V2 over T2 V1. So that would be taking the reciprocals to put 1 over everything. Mathematically, the way that works out, though, is you're just going to flip everything. And so I'm just going to go ahead and do that here. And there we go. So we'll end up with T1 is equal to T2 V1 over V2. And by the way, alternatively, you could have multiplied both sides here by T2 over V2. And then multiplied both sides by T1. And you would end up at the same place that we're at right now. It's just, there's kind of a few slightly different ways of working the algebra, but they all end up at the same place when doing that. And if you're having trouble with this algebra, this has kind of been a sticking point for a few students that I've had over the years. We can talk about it more when we meet together. So we have our equation for T1. So we'll go ahead and plug in what we know. T1 is 273K. V1, 2.8 liters. And then V2 is 2.57 liters. So our liters here cancel out. We are left with Kelvin as our unit, which is good. So 273 times 2.8 divided by 2.57. That gives us 297.4 Kelvin. Which, if we convert that into Celsius, which we would do just by subtracting 273, that is 24.4 Celsius. All right, hopefully that made sense. I know we had a little bit of algebra to work through there. But one more thing before we finish up this video here, I do want to point out that this is a good example of why we actually need to use Celsius, or sorry, you need to use Kelvin and not Celsius, because if we plug in the temperature in Celsius here, that's T2, this becomes 0. And if you remember your high school algebra at all, this is where math gets really mad at us. If we divide by 0, the math will get very, very grumpy with us having 2.57 liters divided by 0. So we need that to be in Kelvin to avoid things like this. So you will never have 0 Kelvin. It's not physically possible. And so that is why we need to, or that's one of the reasons at least, why we need to use Kelvin always when we're doing these types of problems. All right, in the next video we will talk about how moles and pressure are related, and I believe how moles and volume are also related as well. So I'll see you in the next video.